magnetic field due to a circular current carrying loop. That was an axis of the magnetic field, okay, it's an axis. But in this class what we'll do is we'll see what will be the magnetic field at the center of the loop, okay, at the center of the loop if a current is flowing in this loop. So there will be a magnetic field generated around the wire, we know that, and due to that current which is there, the influence of that magnetic field will also be there at the center. So we will see what will be the value of magnetic field at the center of this loop. Now, what we know is magnetic field is equals to, from Biot-Savart law, this is the equation of magnetic field according to Biot-Savart law. Now let us modify this equation according to the figure which is given over there. Now we know that our instead of R, that is the distance between the current element and the place where we are finding the magnetic field. Okay, so this is the portion of that is what we call the current element, and over here we are finding the influence of that magnetic field. So this distance between these two will be A. So instead of R, we can write A square. Okay. Now for angle, let us see what will be the angle between this current element and this point over here. Now current is moving this way. Okay, just if you consider a small section over there, it looks like a straight line. So at this point and the distance over here. So this angle is 90 degree. Your theta will be 90 degree. So theta in this case is 90 degree, and we know that sin 90 is 1. So our dP is equals to mu naught by 4 pi I dl by A square, because our sin theta is 90 degrees, so it will become 1. So instead of that we are writing 1. So this becomes like this. Now to integrate, to find the magnetic field, what we do is we integrate, and when we integrate, all the constant things will be out of the integration. So all these things are constant. If current is constant and if the radius of that is not changing, so it is constant. So we will integrate dl. Now what we have considered is, we have considered a circular current carrying loop, and if it is a circle, when we integrate all the portion of this circle, that means when we add all the portion of this circle, what we get is, we get the circumference, and circumference is 2 pi. So in this case, if radius is A, so it will be 2 pi A. So this becomes B is equals to mu naught by 4 pi I by A square. Integration of this is 2 pi A. That is the circumference of the circle. So from here, what many things we can cancel out. So we will see what we can cancel. 2 pi and pi gets cancelled. A and A square. So let's see what we get at the end. So over here, your B is equals to mu naught by 2. Sorry, pi is not there. 2 pi A. This is what we get, mu naught I by 2A. Okay, this is a value of magnetic field which is due to a current carrying circular loop at the center. Okay, we are considering exactly at the center. Now if this loop has got n number of coil, n number of turns, so if this has n number of turns, what we do is we multiply this equation by n, that is the number of turns. So the magnitude of the magnetic field will be increased by n number. That means more the loop, more the number of turns over here, more will be the influence or the magnetic field. It will be that much stronger. So if there is a single wire, the magnetic field will be less. If there are more number of turns, then we can assume that the strength of the magnetic field is more. Now, few things what we know is, this experiment or these things we have already learned in class 10. Suppose you have a board over here, and if you insert a loop of a wire in this board, and if you try to draw the pattern using the iron fillings, what we can see is the pattern of the magnetic field will be like this. It will be move on to the center, okay, as we move on to the center, the magnetic field at the center will be uniform or the straight line. Similar thing happens over here. Due to this loop also, there are circular magnetic field around this loop, but at the center, the magnetic field will be linear, it will be uniform. So just remember that magnetic field at the center of the loop will be uniform. It will be straight line, it will be uniform. So this is magnetic field at the center of a circular current carrying loop. Now, this was using Biot-Savart's law. Now next we'll study about another law which is more simpler to find the magnetic field. This law is also to find the magnetic field only, but it is simple. So we'll study about that, and that is known as Ampere's law or Ampere's orbital law. Okay, we'll discuss about Ampere's orbital law. Ampere's orbital law. So what this states is the line integral of magnetic field around any closed path. Okay, a line integral of magnetic field, that means if you add the magnetic field around any closed path, then it will be equals to mu naught times the current which is passing in that wire. So if you write this, you can write it like this. Line integral means if you add all the magnetic field in a closed path, we make this integration with the circle over here. It means that we are integrating a closed path. Okay, it should be a closed path. Like in the case of electric field, we have discussed about Gauss law. In magnetic field, the similar case will be Ampere's orbital law. Gauss law and Ampere's orbital law are quite similar to each other. But this is for magnetic field and Gauss law was for electric field. Just try to compare the two equations. So it states that the integration of magnetic field around a line or a closed path equals to mu naught times the current which is flowing in that wire. So magnetic field is generated by current, so mu naught times the current will be the amount of magnetic field generated by that closed path. So this is the Ampere's orbital law. So next what we will do is we will prove this law. Proof of Ampere's orbital law. For that, let me make the diagram. Okay, we consider a wire in which the current is flowing. So we consider a wire XY where the current is flowing. Now due to this, what happens? Magnetic field will be generated around this. So magnetic field will be generated like this. Okay? Circular, concentric circle type of magnetic field will be generated. So we are just trying to prove this law. Now current I is flowing in this wire. So magnetic field will be generated. So we take a small part over here. So that we can denote it as P. Now at this point, this is the radius. Suppose we keep it as R. Okay, R is the radius. Now we take a small portion of the wire, that is dl. Now at this point, what we can see is, okay, first of all let me start with this one. Now first of all, let me write the Biot-Savart law for a long wire. We have already derived the equation. From the Biot-Savart law, we'll derive Ampere's orbital law. So first of all, let me write down Biot-Savart's law. That is for a straight line. Okay, for a straight wire, what will be the Biot-Savart law? It is V is equals to mu naught by 2 pi I by R. This is the Biot-Savart equation of Biot-Savart law for a long straight wire. Now over here, the direction of the magnetic field, if it is like this, direction of magnetic field will be using right hand thumb rule. If it is moving upward, the magnetic field will be the magnetic field is in anti-clockwise direction. It's not straight, it's in anti-clockwise direction. At this point, at this particular point, the direction of the magnetic field will be like this. So in every point, the direction of the magnetic field is changing, but at this point, this will be the direction of the magnetic field. So what we consider is, what we can see over here is direction of dl and and the direction of magnetic field. Direction of this dl and magnetic field are in the same direction. Okay, these two are in the same direction. Okay, at this particular point. So when dl and b are in same direction, what happens? Cos of that will be cos 0 degree. Okay, so sorry, theta will be 0 degree. Now, why am I writing it as 0 degree is, what we know is for a closed path, this is the integration of b dot dl is equals to mu naught I. So we are trying to prove this, so just write this one. So integration of this should be equal to mu naught I. That is what we are going to prove. Now this is a dot product. When you remove a dot product, what we can write is, we can write b dl cos theta. Okay. When we remove a dot, we can write cos theta. When we remove a cross, we can write sin theta. Now, cos 0 degree is 1. So this becomes integration of d dl, because what we know is cos 0 is 1. So when dl and b are in the same direction, what happens? Angle is equal to 0, cos 0 is equal to 1. So when we remove this, what we can write? Cos theta. So cos theta becomes 1. So it is integration of b dl. Now b is magnetic field, which is constant, so integration of dl. So integration of dl, that is, your dl is in a circular path. So what happens when we integrate dl? If it is a circular path, if it is a circle, then integration of dl is the circumference of that particular circle. So integration of dl, this is your 2 pi r. So, okay, now look at this equation. B is from bias of Pascal, it is mu naught by 2 pi I divided by r, and dl is 2 pi r. So we'll just put the value over here. It might be a bit confusing. Just put the value in this. So in place of b, what we are writing is, we are writing, in place of b we write mu naught I divided by 2 pi r. And in place of dl, in place of b we are writing this, in place of dl is 2 pi r. Okay, so this part and this part will be cancelled. So this becomes mu naught to r. So we started with this equation, that is integration of b dot dl. B is this much and dl is 2 pi r. So after substituting, what we get is mu naught into I. So eventually what we have derived is, we have proved that integration of b dot dl is equals to mu naught into I. That is your Ampere circuital law. Now there are various applications of Ampere circuital law. One of the application we'll do today and the rest we'll do in the next class. So first application of Ampere circuital law is magnetic field of a long straight wire. To find the magnetic field using this law, that is BTL is equals to mu naught into I. Okay, application, that is the first one. So the first application of Ampere circuital law, that is number 1. First application is magnetic field due to a magnetic field due to a long straight wire. So we consider a wire where current is flowing, around that magnetic field will be generated. So we similarly take a point over here, that is DL, and this is R. So we will see what happens to the amount of magnetic field at that point, that is what will be the magnetic field due to this wire. So for that we are taking a small point DL, and the distance between, or the radius of this magnetic field will be R. Okay, so what we know is, by some law is, sorry, Ampere's orbital law is B dot dl is equals to mu naught into I. This is your Ampere's orbital law. Now for this one, when we remove dot, what we can write? B dl cos theta is equals to mu naught I. Now let us see first of all what will be theta. This dl and topic also what we have done is this DL and R, this are in the same magnetic field and this pole, that is the magnetic field at this pole, that is B and DL, okay, are in the same direction. Okay, are in the same direction because your length is changing like this and even the magnetic field is in the same direction. So your theta becomes 0. Theta is 0, cos 0 is 90 degree and cos 0 is 1. So we can write B dl. B is constant, all of the integration, only dl will be inside. Now circular path, integration of circular path will be 2 pi r. So we can write 2 pi r is equals to mu naught r, or B is equals to mu naught r divided by 2 pi r. Okay. This will be the amount of magnetic field generated by the straight wire. The same thing we have derived using Biot-Savart law, but it is quite long. If you use the Ampere's orbital law, then this will be much simpler to that. So what Ampere's orbital law does is it just simplifies the way we derive equation for magnetic field. Biot-Savart law is also precise, but this is more precise than Biot-Savart law. It is like this is much more simpler than Biot-Savart law. So this much for today. We'll continue the next class. We'll do few more application of Ampere's orbital law, which is there in the syllabus. This much for today. Thank you.